the most powerful telescope ever built, just looked back in time, and what it found terrifies scientists. Galaxies that should not exist, black holes that grew too fast, stars that may be powered by dark matter itself. The James Webb Space Telescope was launched to answer humanity's oldest questions. Instead, it is raising new ones nobody expected. In the next 2 hours, we will journey to the edge of known reality. If you enjoy this journey, consider liking and subscribing. Now, take a breath. We begin at the beginning, when there was almost nothing at all. On Christmas Day, 2021, a rocket lifted off from the coast of South America. Inside it sat a machine that would change everything humanity knows about the cosmos. The James Webb Space Telescope, the most expensive scientific instrument ever constructed. A golden mirror the size of a tennis court, folded like origami, launched into the void with one mission: look back in time, find the first light, show us where we came from. For 30 days, scientists held their breath. The telescope had to travel nearly 1 million miles from Earth. It had to unfold itself perfectly in the freezing darkness of space. 300 single points of failure. Any one of them could end the mission forever. It worked. By summer of 2022, the telescope opened its eyes, and immediately, something was wrong. The first deep field images arrived. Scientists gathered around their screens, expecting to see faint smudges of light. Tiny, dim, primitive galaxies from the edge of time. The infant universe, still learning how to build. Instead, they saw giants, massive galaxies, bright galaxies. Galaxies filled with billions of stars, arranged in complex spirals, burning with the light of mature cosmic cities. These objects looked like they belonged in the modern universe, but they existed when the cosmos was barely 300 million years old. To understand why this is terrifying, imagine digging in the desert and finding a smartphone buried beneath ancient Roman ruins. Something that advanced should not exist at that point in history. The timeline does not allow it. The same principle applies here. Galaxies need time to form. Gas must collapse under gravity. Stars must ignite, burn, and die. Heavy elements must be forged and scattered. Generations of stellar death and rebirth must cycle before a galaxy can look mature. Scientists had calculated how long this process takes. Billions of years, not hundreds of millions. Yet here they were, cosmic cities fully built when the universe was still in its infancy. One astronomer described the feeling to colleagues. He said it was like finding a 6-foot-tall toddler. The proportions do not make sense. The math does not work. Something fundamental about our understanding must be wrong. Within months, the discoveries kept coming. More massive early galaxies, then more, then hundreds. The James Webb Space Telescope was not finding one or two strange exceptions. It was finding them everywhere it looked. Papers flooded scientific journals. Words like crisis and impossible appeared in titles. Nobel Prize-winning physicists admitted publicly that the standard model of cosmology might need to be rewritten. The standard model is not some rough guess. It is the framework that explains nearly everything about the universe. How it began, how it expanded, how matter clumped together into stars and galaxies over billions of years. This model has been tested and refined for decades. It predicted the cosmic microwave background radiation with stunning accuracy. It told us the age of the universe down to the nearest 100 million years. And now, a single telescope was suggesting it might be incomplete, or worse, fundamentally flawed. Scientists are careful people. They do not panic over one strange observation. But when the strange observations keep piling up, when every new data release brings more impossible objects, the conversation changes. We are no longer asking if something unexpected happened in the early universe. We are asking what it was, and whether our entire picture of cosmic history needs to be torn down and rebuilt from scratch. This is confirmed. The galaxies are real. The measurements have been checked and rechecked by independent teams around the world. Whatever explanation emerges, it must account for objects that should not exist when they do. But the galaxies were only the beginning, because lurking inside some of them, Webb found something even harder to explain. Black holes, supermassive ones, and they were already ancient when the universe was still young. In January of 2024, astronomers pointed the James Webb Space Telescope at a tiny patch of sky. They were hunting for the most distant objects in existence. What they found shattered every previous record. A galaxy, designated with a string of letters and numbers. Scientists simply call it the record holder. It existed just 290 million years after the Big Bang. To put that in perspective, the universe is nearly 14 billion years old. This galaxy appeared when the cosmos had lived only 2% of its current age. Light from this object traveled for over 13 billion years to reach us. When that light began its journey, Earth did not exist. Our solar system would not form for another 9 billion years. The Milky Way itself was still assembling from smaller fragments scattered across an expanding void. And yet this ancient galaxy was not primitive. It was not a faint wisp of glowing gas struggling to hold itself together. It stretched across 1,600 light-years. It contained hundreds of millions of stellar masses worth of material. It was bright, mature, complex. One researcher compared the discovery to excavating ancient ruins and finding a modern cell phone buried in the dirt. The object did not belong in that era of history, but there it was, confirmed by nearly 10 hours of spectroscopic observation. The spectrum is crucial. It acts like a cosmic fingerprint, revealing exactly how far away an object is and what it contains. When scientists analyzed the light, they found the telltale signature of redshift at 14.32. This number represents how much the universe has stretched since that light was emitted. The higher the number, the older and more distant the source. Before this discovery, the previous record holder had a redshift of 13.2. That galaxy existed roughly 325 million years after the Big Bang. The new discovery pushed the boundary back by another 35 million years. That might sound small, but in the early universe, every million years matters enormously. Stars need time to form. Gas clouds must collapse. Nuclear fusion must ignite. And here was a galaxy with hundreds of millions of stellar masses already assembled, burning brightly when the universe was barely old enough to have produced its first generation of stars at all. The research team was stunned. One scientist admitted that nobody had dreamed there would be galaxies this bright at this high a redshift. The observation defied expectations built over decades of theoretical modeling. But there is something even stranger. The light from this galaxy showed traces of dust. Dust is made of heavy elements: carbon, silicon, iron. These elements do not exist at the beginning of time. They are forged inside stars and scattered into space when those stars explode. For dust to exist in this galaxy, entire generations of massive stars must have already lived and died. That process alone should take hundreds of millions of years. Yet here was dust. 290 million years into cosmic history. Scientists have a phrase for discoveries that challenge established theory. They call them tension with the Standard Model. But this was not tension. This was a crack running through the foundation. The discovery has been confirmed by multiple independent analyses. There is no measurement error. The galaxy is real, and it is exactly as old and as massive as the data suggests. Researchers believe this is only the beginning. Webb is capable of seeing even further back in time, perhaps to within 120 million years after the Big Bang. If galaxies this massive exist at 290 million years, what else might be waiting in the darkness beyond? But distance records are only part of the story. Because while astronomers were finding these impossible galaxies, they also started noticing something hiding inside them. Engines of destruction, gravitational monsters, already fully grown. At the center of nearly every large galaxy sits a monster, a supermassive black hole, millions or billions of times heavier than a single star. These objects warp space so severely that nothing escapes their grip. Not matter, not light, not time itself. Scientists thought they understood how these monsters formed, slowly, patiently, over billions of years. First, a massive star would explode and leave behind a small black hole. That black hole would merge with others. It would swallow gas and dust from its surroundings. Generation after generation, it would grow. Eventually, after billions of years of feeding and merging, it would reach supermassive status. The James Webb Space Telescope proved this timeline wrong. In galaxy after galaxy from the early universe, Webb found supermassive black holes already in place, not small seeds waiting to grow. Fully formed giants. Some weighed billions of times more than a typical star, and they existed when the universe was less than 1 billion years old. This is confirmed by spectroscopic observation. When gas falls toward a black hole, it heats up and emits light in specific patterns. Scientists can read these patterns, like a signature, identifying the presence of an actively feeding black hole and estimating its mass. The numbers did not add up. Black holes this massive should not exist this early. Even if a black hole fed continuously at the maximum possible rate, gobbling matter as fast as physics allows, it still could not reach these sizes in the time available. There is a speed limit for black hole growth. When a black hole feeds too aggressively, the radiation it emits pushes away the incoming material. This creates an outward pressure that limits how fast the black hole can consume. Scientists call this the Eddington limit. To reach billions of stellar masses within a few 100 million years, these early black holes would need to exceed that limit dramatically. They would need to feed in ways that current physics struggles to explain. One team found a black hole in a galaxy that existed just 570 million years after the Big Bang. The black hole was actively growing, devouring material at a furious rate. But the truly shocking detail was the ratio between the black hole and its host galaxy. Normally, a supermassive black hole makes up a small fraction of its galaxy's total mass. The two grow together in lockstep over cosmic time. But this early black hole was overmassive. It was far too heavy compared to the stars around it. The relationship astronomers assumed existed between black holes and galaxies was inverted. This suggests something profound. Black holes may have formed first. They may have grown faster than the galaxies surrounding them. The entire sequence of cosmic construction might be backwards from what textbooks describe. Some theorists propose that the first black holes did not form from dying stars at all. They may have collapsed directly from massive clouds of primordial gas. These direct collapse black holes could have started much heavier than ordinary stellar remnants, giving them a head start in the race to supermassive status. Others suggest that exotic physics played a role. Perhaps the early universe had conditions that allowed black holes to exceed the Eddington limit. Perhaps dark matter interactions seeded unusually large black holes before galaxies even began to form. None of these ideas are confirmed yet. They are theories attempting to explain observations that current models cannot accommodate. The mystery remains open, and every new Webb observation adds more data to the puzzle. But the black holes were not alone. Surrounding them, astronomers found strange objects that do not fit any known category. Red, compact, and impossibly abundant. They call them the little red dots, and they are everywhere. Less than 6 months after the James Webb Space Telescope began its science mission, astronomers noticed something unusual in the data. Scattered across deep field images were small, red, compact objects. Dozens of them at first, then hundreds, now thousands. They call them little red dots, and nobody fully understands what they are. These objects are red because their light has traveled so far through expanding space that it has stretched into longer wavelengths. The farther light travels, the more it stretches, shifting from blue to red and eventually into infrared. This process is called redshift, and it tells astronomers how distant an object is. The little red dots are extremely distant. Most of them existed within the first 1.5 billion years after the Big Bang. They are relics from an era when the universe was still assembling its first cosmic structures. But their abundance is the first mystery. Before Webb, astronomers did not expect to find so many compact, luminous objects at these extreme distances. The standard model of cosmology predicted a younger, simpler universe with fewer bright sources. Instead, Webb found the sky littered with these strange red points. The second mystery is their nature. At first, scientists assumed the little red dots were compact galaxies with active black holes at their centers. When matter falls into a black hole, it forms a swirling disk that heats up and glows brightly. This glow can outshine all the stars in a galaxy combined. Spectroscopic observations seem to support this idea. Many little red dots show signatures of gas moving at extreme speeds, roughly 2 million miles per hour, orbiting something incredibly massive at their core. This is exactly what astronomers expect to see around a feeding supermassive black hole, but some observations do not fit. The ratio between certain wavelengths of light is strange. The dust content is unusual. The relationship between the black hole mass and the surrounding galaxy mass is often inverted, with black holes that appear far too heavy for their hosts. Some researchers now suspect that not all little red dots are galaxies at all. They may represent an entirely new class of cosmic object, something that forms only in the extreme conditions of the early universe and does not have a modern equivalent. One hypothesis involves black hole stars. These would be objects where a black hole sits at the center of a dense cloud of gas, feeding continuously while the surrounding material glows with intense radiation. The black hole and the gas would form a single luminous unit, unlike anything in the nearby universe. Another hypothesis involves dark stars. These are hypothetical objects powered not by nuclear fusion but by the annihilation of dark matter particles. If dark matter exists in certain forms, it could collide with itself and release energy, heating a primordial gas cloud into a massive, glowing sphere. Such objects could explain the unusual brightness of the early universe, without requiring mature galaxies to exist so soon after the Big Bang. Neither hypothesis is confirmed. Both are theoretical attempts to explain observations that do not match existing models. What scientists do know is that approximately 70% of the little red dots they have examined show clear signs of actively feeding black holes. This hints at an era of hidden black hole growth in the early universe, a period when these gravitational monsters were bulking up behind veils of gas and dust, invisible to previous telescopes. The implications are enormous. If black holes were growing this aggressively, this early, they may have shaped the evolution of galaxies in ways we never anticipated. They may have influenced star formation, chemical enrichment, and the distribution of matter across cosmic structures. But explaining the little red dots requires understanding what fueled them. And that brings us to an even deeper question. What were the very first stars like? And did they even work the way stars work today? Before there were galaxies, there were stars. The very first generation of stars ever created. Scientists call them population 3 stars. And for decades, they existed only in theory. The universe began with hydrogen, helium, and trace amounts of lithium, nothing else. Every other element on the periodic table was forged later, inside stars. Carbon, oxygen, iron, gold, all of it cooked in stellar furnaces and scattered into space when those stars died. Population 3 stars would have been the first furnaces. Made entirely of primordial gas, they had no heavy elements to help regulate their formation. Without heavier atoms to cool collapsing gas clouds efficiently, these first stars would have grown enormous. Computer simulations suggest they could have reached 100 times, 1,000 times, perhaps even 100,000 times the mass of our own star. Such monsters would have burned hot and bright, flooding the early universe with ultraviolet radiation. They would have lived fast and died young, exploding as supernovae after only a few million years. Their deaths would have seeded the cosmos with the first heavy elements, making the next generation of stars and eventually planets possible. But no one has ever seen a population 3-star directly. They lived and died billions of years ago in an era so distant that their light has stretched into infrared wavelengths invisible to most telescopes. The James Webb Space Telescope was built, in part, to find them, and recent observations suggest it may have succeeded. In a distant galaxy, observed through gravitational lensing, astronomers detected a faint light signature consistent with population. 3 predictions. The galaxy, designated with the code name LAP-1b, showed an unusual lack of heavy elements. Its light matched theoretical models for stars made almost entirely of hydrogen and helium. The discovery is not yet confirmed beyond doubt. Scientists remain cautious because the observations are at the edge of Webb's detection capabilities. The faint signal could also be explained by unusually pristine clouds of gas rather than actual stars. Deeper observations are needed to settle the question, but this is the closest anyone has come to seeing the first generation of stars. If confirmed, it would answer one of the oldest questions in astronomy. How did the first light switch on? A second galaxy, called GNZ11, has also shown hints of population 3 stars. This galaxy existed just 430 million years after the Big Bang. Spectroscopic data revealed strange chemical signatures, including unusually high levels of nitrogen compared to oxygen. This ratio matches what theoretical models predict would remain after massive primordial stars exploded. The evidence is mounting, but not yet definitive. What makes this search difficult is that population 3 stars were likely rare, even in the early universe. They would have formed in isolated pockets of pristine gas, far from regions already polluted by previous stellar deaths. Finding them requires looking at exactly the right place at exactly the right time in cosmic history. Gravitational lensing helps. When a massive galaxy cluster sits between Earth and a distant object, its gravity bends and magnifies the light from behind. This turns galaxy clusters into natural telescopes, boosting the brightness of faint sources by factors of 10, 50, sometimes over 100. Webb has used this technique to study some of the faintest and most distant objects ever observed. Individual stars in galaxies billions of light years away have been detected through these cosmic magnifying glasses. If population 3 stars truly existed as predicted, they would have left specific chemical fingerprints. Finding those fingerprints would confirm that the first chapter of cosmic history unfolded as theorists imagined. But some researchers are exploring a stranger possibility. What if the first stars were not powered by nuclear fusion at all? What if something far more exotic kept them burning? Every star you have ever seen works the same way. Hydrogen atoms crash together under immense pressure and fuse into helium. This nuclear reaction releases energy. That energy pushes outward, balancing the inward pull of gravity. The star shines. But in the very early universe, something different may have happened. Some of the first luminous objects may not have been fusion-powered stars at all. They may have been dark stars, fueled by the annihilation of dark matter. Dark matter makes up roughly 25% of the universe. It does not emit light. It does not absorb light. It interacts with ordinary matter only through gravity. Scientists know it exists because galaxies rotate faster than they should based on visible matter alone. Something invisible is providing extra gravitational pull. The leading candidates for dark matter particles are called weakly interacting massive particles. If these particles exist and occasionally collide with each other, they annihilate. When they annihilate, they release energy. In the dense centers of the first collapsing gas clouds, dark matter particles would have been packed tightly together. Collisions would have been frequent. The energy released by those collisions could have heated the gas, preventing it from collapsing all the way into a compact star. The result would be a dark star. a massive, puffy sphere of hydrogen and helium kept warm not by fusion but by dark matter annihilation at its core. Such an object could grow enormous, perhaps millions of times the mass of a typical star, while remaining relatively cool at its surface. This is a theoretical prediction, not a confirmed observation. But the James Webb Space Telescope may have found evidence supporting it. Several of the brightest early galaxies Webb observed have unusual properties. They are too luminous to be explained by ordinary star populations. Their colors and spectra do not match standard stellar models. Some researchers have proposed that these galaxies contain dark stars, objects so massive and bright that they dominate the light output of their entire host. If dark stars existed, they would eventually run out of dark matter fuel. When that happened, they would collapse. A dark star millions of times heavier than an ordinary star would not end as a normal supernova. It would collapse directly into a black hole, a very massive black hole. This provides a potential solution to one of Webb's biggest mysteries. How did supermassive black holes grow so large so quickly? If dark stars created unusually heavy black hole seeds at the dawn of time, those seeds would have had a head start in the race to supermassive status. The connection between dark stars and early black holes is speculative but intriguing. It links two separate puzzles, the impossible brightness of early galaxies and the impossible size of early black holes, into a single narrative. Confirming dark stars would have profound implications. It would provide the first direct evidence for a specific type of dark matter particle. It would reveal that the early universe operated under physical conditions dramatically different from today, and it would force astronomers to rewrite the first chapter of stellar history. Current observations are not conclusive. The bright early objects Webb has found could also be explained by rapid bursts of ordinary star formation, or by feeding supermassive black holes hidden behind dust. Distinguishing between these possibilities requires more data and more sophisticated analysis. But the search continues. Every new Webb observation pushes deeper into the past. Every strange signal raises the question anew. Were the first lights in the cosmos powered by darkness itself? And speaking of darkness, the early universe held other secrets. Massive stars, far heavier than any in the modern cosmos. Monsters that may have left fingerprints in ancient light. The largest stars in the present-day universe weigh perhaps 200 times more than our own star. They burn blue hot and die in spectacular explosions after only a few million years. By cosmic standards, they are extreme outliers. But in the early universe, stars may have grown far larger. Theoretical models predict that primordial gas clouds could have produced monsters weighing 10,000, even 100,000 stellar masses. Objects so massive they would reshape our understanding of stellar physics. Such stars would have lived extraordinary, brief lives. Their cores would burn through fuel at a furious pace, fusing hydrogen to helium to carbon to oxygen in rapid succession. Within a few million years, perhaps less, they would face their end. What happens when a star this massive dies? For most large stars, the answer is a supernova. The core collapses, rebounds, and blasts the outer layers into space. But for the true monsters, the ending might be different. They might skip the explosion entirely. A star heavier than roughly 260 stellar masses can collapse directly into a black hole without producing a supernova at all. The gravity is so intense, the collapse so rapid, that no shockwave escapes. The entire star simply vanishes behind an event horizon, leaving behind a black hole far heavier than any formed through ordinary channels. This process is called direct collapse, and it may explain the supermassive black holes Webb has found in the early universe. If monster stars existed in the first few 100 million years after the Big Bang, their direct collapse remnants could have provided the seeds for rapid black hole growth. Starting with a black hole, already weighing thousands or tens of thousands of stellar masses, gives it an enormous head start. Subsequent feeding and merging could then build it up to billions of stellar masses within the available time. Recently, astronomers found potential evidence for these monster stars. A distant galaxy, observed by Webb, showed an unusual chemical signature. The ratio of nitrogen to oxygen was far higher than normal stellar processes produce, but it matches precisely what theoretical models predict from the winds of extremely massive primordial stars. The galaxy, catalogued as GS3073, also contains an actively feeding black hole at its center. This black hole could be the remnant of one of those ancient monsters. The chemical fingerprint and the black hole together form a coherent picture of how the first gravitational giants came to be. This evidence is compelling, but not yet conclusive. Other processes can produce unusual nitrogen to oxygen ratios. More observations are needed to rule out alternative explanations and confirm that monster stars truly existed. If confirmed, the implications reach beyond astronomy. These stars would have dominated the energy output of the early universe. Their radiation would have ionized the surrounding gas, ending the cosmic dark ages and allowing light to travel freely through space. Their deaths would have seeded the cosmos with the first heavy elements, making planets like Earth possible billions of years later. We exist because stars died. Monster stars dying in the first few 100 million years of cosmic history may have set the entire chain of events in motion. The James Webb Space Telescope is peeling back layer after layer of this ancient story. Each observation adds detail to a picture that once existed only in theoretical speculation. But the early universe held still more surprises. Some galaxies Webb found are not just massive, they are structured in ways that should have taken far longer to develop. When you picture a galaxy, you probably imagine a spiral, a pinwheel of stars with graceful arms sweeping outward from a bright central core. The Milky Way is a spiral. So is our nearest large neighbor, Andromeda. Spirals are among the most beautiful structures in the cosmos. They are also supposed to take a long time to form. Spiral arms are density waves, regions where stars and gas bunch together temporarily as they orbit the galactic center. Creating and maintaining these patterns requires a galaxy to settle into a stable rotating disk. That process takes time. Gas must collapse. Stars must form. The galaxy must survive collisions and mergers that would disrupt its delicate structure. Astronomers estimated that spiral galaxies could not appear until several billion years after the Big Bang. The early universe was too chaotic, too violent, too crowded for such elegant forms to survive. The James Webb Space Telescope proved them wrong. In image after image from the early cosmos, Webb found spiral galaxies, not fuzzy irregular blobs, but clear spiral structures with defined arms. Some of these galaxies existed when the universe was less than 2 billion years old. A few appeared even earlier. One particularly striking example is nicknamed the Big Wheel. This galaxy existed roughly 2 billion years after the Big Bang, in an era when spirals were thought to be rare or non-existent. Yet it displays a clear spiral pattern, with dust lanes and star-forming regions distributed along sweeping arms. Even more puzzling, the Big Wheel appears to have survived encounters with other galaxies. Its environment suggests it has experienced collisions or close passes. Normally, such interactions would destroy spiral structure, smearing the delicate arms into a featureless, elliptical shape. Yet the spiral persists. This suggests that galaxies in the early universe may have grown through processes we do not fully understand. Perhaps they assembled more smoothly, with less violent merging. Perhaps the conditions of the early cosmos allowed spiral patterns to form more quickly than modern simulations predict. Another early spiral, imaged previously by the Hubble Space Telescope, was thought to be an irregular smudge. Webb's sharper infrared vision revealed the truth. Hidden beneath the blur was a distinct spiral lattice, a complex shape that astronomers assumed the young universe could not produce. The existence of early spirals does not overturn cosmology by itself. It does, however, add to the growing list of observations that challenge the standard timeline. Galaxies are more mature, more structured, and more abundant in the early universe than models predicted. Scientists are now working to understand how these spirals formed so quickly. Some propose that dark matter halos in the early universe were smoother than expected, allowing gas to settle into rotating disks without disruption. Others suggest that the first stars formed in ways that promoted rapid disk assembly. None of these explanations are fully confirmed. The mystery of early spiral galaxies remains open. What is clear is that the young universe was far more organized than anyone anticipated, and the structures extend beyond individual galaxies. Webb has revealed something happening on the largest scales of existence. A coordinated pattern that hints at secrets buried in the fabric of reality itself. Here is something that should keep you awake at night. The universe might be rotating. Not individual galaxies, the entire universe, all of it, spinning on an axis that has persisted since the moment of creation. This idea sounds absurd. The Big Bang is supposed to have been an explosion in all directions simultaneously, with no preferred orientation. The universe should be the same no matter which way you look. This principle is called isotropy, and it forms one of the foundational assumptions of modern cosmology. But recent observations from the James Webb Space Telescope have raised unsettling questions. An analysis of over 260 galaxies from the JADES survey found an unexpected pattern. Galaxies were not spinning randomly. More of them seemed to rotate in one direction than the other. The imbalance was small but statistically significant, suggesting that something influenced the rotation direction of galaxies across vast regions of space. What could cause such a pattern? Two possibilities stand out. The first involves the large-scale structure of the universe. Galaxies do not form in isolation. They condense from cosmic filaments, enormous threads of dark matter and gas that stretch across millions of light years. If these filaments have a subtle twist or alignment, they could imprint a preferred rotation direction on the galaxies that form within them. The second possibility is more radical. The universe itself might have been born rotating. If the cosmos spun during its earliest moments, that spin could have been preserved and amplified as matter collapsed into galaxies. Galaxies would then inherit a rotational preference from the universe that created them. How could the universe be born spinning? One theoretical framework involves black holes. Specifically, the idea that our entire observable universe might exist inside a rotating black hole. This is a speculative hypothesis, not an established theory, but it has been explored by physicists for decades. If the Big Bang occurred within a spinning singularity, the interior space would inherit angular momentum. Everything inside would tend to rotate in the same direction. The James Webb observations do not prove this hypothesis. They raise it as a possibility worth investigating. The pattern could also result from systematic errors in how the data was collected and analyzed. More observations are needed to determine whether the rotational imbalance is real. If it is real, the implications are staggering. It would mean the universe has a special direction. Cosmology would need to incorporate this asymmetry into its models. Our understanding of the Big Bang itself would require revision. The study is ongoing. Scientists are examining larger samples of galaxies and refining their statistical methods. Whatever the outcome, the question is now on the table in a way it never was before. The James Webb Space Telescope was built to see the first light. Instead, it keeps revealing that the cosmos is stranger than anyone imagined. Galaxies that formed too fast, black holes that grew too large, structures that organized too early, and now, perhaps, a universe that has been spinning since the beginning of time. But there is another mystery Webb is helping to solve. Something invisible that shapes everything we see. You cannot see dark matter. No telescope can image it directly. It does not glow, reflect, or absorb light. Yet it outweighs all the visible matter in the universe by a factor of 5 to 1. Without it, galaxies would fly apart. Stars would never have formed, Neither would you. Scientists know dark matter exists because of its gravitational effects. Galaxies rotate faster than they should based on visible mass alone. Galaxy clusters bend light more strongly than their stars, and gas can explain. The cosmic web of filaments connecting galaxies across millions of light years would collapse without dark matter scaffolding. But the nature of dark matter remains one of the deepest mysteries in physics. Is it made of particles? If so, what kind? How do those particles behave? Do they interact with each other, or only with ordinary matter through gravity? The James Webb Space Telescope is providing new clues. When Webb images distant galaxies, it captures their shapes in unprecedented detail. And those shapes contain information about dark matter. Specifically, the way young galaxies look can reveal how dark matter clumped together in the early universe. Recent observations found something unexpected. Many young galaxies, from the first 1 to 3 billion years after the Big Bang, are elongated. They look like cosmic pickles, stretched along one axis, rather than forming round blobs or flat disks. This is significant because different types of dark matter produce different structures. The standard model assumes cold dark matter, made of heavy, slow-moving particles that clump densely on small scales. Cold dark matter simulations predict that early galaxies should look relatively round, but there are alternative models. Warm dark matter consists of lighter particles that move faster and smooth out small-scale clumps. Wave, or fuzzy, dark matter consists of extremely light particles that behave more like waves than individual points. Both alternatives produce smoother filaments in the cosmic web, which could lead to elongated young galaxies. The elongated shapes Webb observed match warm and fuzzy dark matter predictions better than cold dark matter predictions. This does not prove that cold dark matter is wrong, but it opens the door to alternative models that were previously disfavored. If dark matter is warm or fuzzy, it would change our understanding of how structures formed in the early universe. The first stars and galaxies would have assembled differently. The distribution of matter on large scales would follow different patterns. The entire history of cosmic evolution would need adjustment. Confirming these results requires more data. Webb is still surveying distant galaxies, building a statistical picture of their shapes and properties. Ground-based telescopes and future space missions will add complementary observations. What is clear is that dark matter is no longer just a background player in cosmology. It is an active participant whose nature shapes everything we see. The James Webb Space Telescope is turning an invisible ingredient into a visible signature, written in the elongated forms of the earliest galaxies. But dark matter is not the only invisible force at work. There is another mystery tearing the universe apart at its seams. The universe is expanding. This has been known for nearly a century, ever since astronomers noticed that distant galaxies are moving away from us. The farther away a galaxy is, the faster it recedes. Space itself is stretching, carrying galaxies along with it like raisins in rising dough. The rate of this expansion is called the Hubble constant. Measuring it precisely is one of the most important tasks in cosmology. The number tells us the age of the universe, its size, and its ultimate fate. There is just one problem. Two different methods of measuring the Hubble constant give two different answers, and neither method appears to be wrong. The first method looks at the distant past. Scientists study the cosmic microwave background, the faint radiation left over from when the universe was only 380,000 years old. By analyzing the patterns in this radiation, they can calculate how fast the universe should be expanding today. This approach gives a Hubble constant of roughly 67 kilometers per second per megaparsec. The second method looks at the nearby universe. Scientists measure the distances to stars and galaxies using a chain of techniques called the cosmic distance ladder. By combining these distances with measurements of how fast those objects are moving away, they calculate the expansion rate directly. This approach gives a Hubble constant of roughly 73 kilometers per second per megaparsec. A difference of 6 may not sound like much, but in precision cosmology, it is enormous. The two numbers disagree by more than can be explained by measurement uncertainty. At least one of them must be missing something fundamental. This discrepancy is called the Hubble tension. When it first emerged, some scientists hoped it was a measurement error. Perhaps the first rung of the cosmic distance ladder was calibrated incorrectly. Perhaps the cosmic microwave background analysis had unrecognized flaws. The James Webb Space Telescope was called in to settle the debate. Webb's sharper vision allowed astronomers to recheck the distance measurements with unprecedented accuracy. They looked at pulsating stars called Cepheids, which serve as standard candles for measuring cosmic distances. They examined the same galaxies Hubble had observed and compared the results. The verdict: Hubble was right. The distance measurements were accurate. There was no error large enough to explain the tension. This means the Hubble tension is real. The universe is expanding faster in the nearby cosmos than models of the early universe predict. Something is missing from our understanding. What could it be? Theorists have proposed numerous possibilities. Perhaps there was a brief burst of extra energy in the early universe that accelerated expansion temporarily. Perhaps dark matter has properties we have not accounted for. Perhaps dark energy, the mysterious force driving cosmic acceleration, behaves differently than assumed. A Nobel Prize-winning physicist called this situation a crisis. Not a tension, not a puzzle, but a crisis. The standard model of cosmology, which has successfully explained countless observations, cannot accommodate this discrepancy without significant revision. Webb continues to gather data. Each new measurement adds precision to the numbers. Whatever resolution emerges, it will likely require new physics, something beyond what current theories describe. The universe is hiding secrets, and the more precisely we measure, the stranger those secrets become. In March of 2025, a flash of high-energy radiation crossed the detectors of a space-based observatory, gamma rays, the most powerful form of light in the universe, coming from unimaginably far away. Within hours, telescopes around the world turned toward the source. Automated alerts triggered observations across every wavelength of light. The race was on to identify what had exploded. The James Webb Space Telescope joined the effort. Using its infrared instruments, it peered through the glare and found the aftermath: a supernova, the explosive death of a massive star. But this was no ordinary stellar corpse. This supernova occurred when the universe was only 730 million years old. It is the most distant stellar explosion ever confirmed, pushed back into the era of cosmic reionization when the first stars and galaxies were just beginning to light up the void. Supernovae are common. Roughly one star explodes somewhere in the observable universe every second. But detecting them at such extreme distances is extraordinarily difficult. Their light is faint, stretched into infrared by cosmic expansion, and often obscured by dust. This particular supernova announced itself with a gamma-ray burst. Gamma-ray bursts are the most powerful explosions in the universe, briefly outshining entire galaxies. They occur when certain massive stars collapse, shooting jets of radiation outward at nearly the speed of light. If one of those jets points toward Earth, we see the flash. The gamma-ray burst provided a beacon. Once astronomers knew where to look, Webb's infrared eyes found the glowing remnant. Spectroscopic analysis confirmed the distance, placing the event firmly in the early universe. This discovery matters for several reasons. First, it proves that massive stars existed and died within the first billion years of cosmic history. Their explosions would have scattered heavy elements into surrounding gas, enriching future generations of stars and making rocky planets possible. Second, it provides a probe of the early universe's conditions. The light from the supernova traveled through intergalactic gas for over 13 billion years. By studying how that light was absorbed along the way, astronomers can map the distribution of matter in the young cosmos. Third, It demonstrates Webb's capability to respond quickly to unexpected events. Transient phenomena, like supernovae, fade rapidly. Catching them requires fast coordination between observatories. Webb proved it can pivot from planned observations to urgent targets in a matter of days. The supernova has been designated with a string of letters and numbers, but scientists sometimes refer to it by the date of its discovery. It represents a milestone in time-domain astronomy, the study of objects that change or move. More discoveries like this will follow. Webb is surveying the sky continuously, and automated systems are improving their ability to flag unusual events. Each ancient supernova found adds another data point to our understanding of how stars lived and died in the early universe. The first generation of massive stars died in explosions that shaped everything that came after. We are now, for the first time, witnessing those deaths directly. But supernovae are not the only violent events Webb has captured. There are other explosions, other cataclysms, other monsters on the move. Black holes are not supposed to move. They sit at the centers of galaxies, anchored by gravity, holding everything around them in orbit. They are the still points around which entire cosmic systems revolve. But one black hole is running, and it is dragging a trail of stars behind it. In early 2025, the James Webb Space Telescope confirmed the existence of what astronomers call a runaway supermassive black hole. This object is hurtling through space at roughly 2 million miles per hour, fast enough to cross the distance from Earth to the Moon in about 7 minutes. How does something that massive move that fast? The leading explanation involves a cosmic collision. When two galaxies merge, their central black holes sink toward the combined center. Eventually, they spiral together and merge into a single, larger black hole. But if a third black hole is present, the gravitational interaction becomes chaotic. One of the three can be flung outward at tremendous speed, ejected from the system entirely. This is what appears to have happened. The runaway black hole was likely kicked out during a triple black hole encounter. It is now plowing through intergalactic space, carrying a trail of gas and stars that it pulled from its former home. The trail is the key evidence. Behind the speeding black hole stretches a thin streak of glowing material, roughly 200,000 light-years long. New stars are forming in this wake, ignited by shockwaves as the black hole plows through ambient gas. Previous observations by the Hubble Space Telescope first spotted this streak, but the nature of the object was uncertain. It could have been a peculiar jet from an active galaxy, or an unusual tidal stream from a galactic collision. Webb's infrared sensitivity and sharper resolution allowed astronomers to rule out alternative explanations. The spectrum confirmed the presence of a compact, massive object at the head of the streak. The velocity measurements matched predictions for a black hole ejected through gravitational slingshot. The discovery is now considered confirmed. This is the first definitive detection of a runaway supermassive black hole. Theoretical models predicted such objects should exist, but finding one required the right combination of luck and technology. The implications are significant. If runaway black holes are common, they could explain some of the missing mass in the universe. They could also pose risks, though extremely remote, to any planetary systems in their path. A supermassive black hole passing through a galaxy would disrupt stellar orbits and potentially trigger waves of star formation or destruction. The runaway will not threaten Earth. It is far too distant, located billions of light-years away. What it does provide is a window into the violent dynamics of galaxy mergers, events that have shaped the cosmos since the first structures formed. Webb continues to study this object and search for others like it. Each runaway black hole found tells a story of cosmic collisions and gravitational chaos, forces that sculpted the universe into its present form. The cosmos is not a peaceful place. It is full of motion, violence, and transformation. And some of that violence is happening closer to home than you might expect. You might think the space between stars is empty, a perfect vacuum stretching between distant points of light, but it is not empty at all. The interstellar medium is filled with gas, dust, and structures so faint that previous telescopes could barely detect them. The James Webb Space Telescope has revealed this hidden realm in unprecedented detail, and what it found surprised even experienced astronomers. In a region near the constellation Cassiopeia, Webb captured light echoes from an ancient supernova. When a star explodes, the initial flash travels outward through space. If that flash encounters clouds of dust, the dust glows briefly in infrared before fading. These light echoes are rare and fleeting, but they illuminate the material between stars. What Webb saw were thin sheets of dust, packed tightly together, showing structure on scales never observed before. The filaments measured only a few hundred astronomical units across, less than 1/100th of a light year. An astronomical unit is the distance from Earth to our star. These sheets were thinner than the size of a small solar system. Astronomers did not know interstellar dust had structure this fine. Previous models treated the interstellar medium as a smooth, diffuse fog. Webb proved it is actually layered and textured, shaped by forces we are only beginning to understand. The most likely explanation involves magnetic fields. The galaxy is threaded with weak magnetic fields that guide the motion of charged particles and dust grains. These fields could organize dust into sheets and filaments, creating the intricate patterns Webb observed. Understanding interstellar dust matters because dust affects almost everything astronomers try to observe. Distant galaxies appear dimmer and redder because dust absorbs and scatters their light. Star-forming regions are hidden behind curtains of dust that only infrared telescopes can penetrate. The chemical evolution of the cosmos depends on dust grains, which serve as catalysts for molecular reactions in cold space. If dust is more structured than assumed, models of all these processes may need revision. The amount of light absorbed by dust along any line of sight depends on how clumpy or smooth the dust distribution is. Getting this wrong affects measurements of distances, luminosities, and chemical compositions throughout the universe. Webb's observations also revealed knots and clouds within the interstellar sheets. These denser regions could be the seeds of future star formation, tiny concentrations of material that will eventually collapse under their own gravity and ignite nuclear fusion. The cosmos is not just vast, it is intricate. Every cubic light year contains structures within structures, patterns within patterns, down to scales that challenge our instruments to detect. Webb is pushing the boundaries of what we can see, revealing complexity where we once assumed simplicity. But the interstellar medium is just one layer of hidden architecture. The universe has surprises at every scale, from the smallest dust grains to the largest structures ever discovered. In 2025, astronomers at the University of Missouri published a discovery that captured attention worldwide. Using the James Webb Space Telescope, they had identified 300 objects in the distant universe that defied explanation. These were not ordinary galaxies. They were too bright. Their light signatures did not match any known category of cosmic object. They appeared to come from the earliest epoch of the universe, yet they outshone everything around them. The researchers used a technique called dropout analysis to find these objects. When light from the early universe travels across billions of light years, it passes through clouds of neutral hydrogen gas. This gas absorbs specific wavelengths, causing distant objects to drop out of visibility in certain filters. By comparing images taken through different filters, astronomers can identify objects at extreme distances based on where their light disappears. The 300 objects passed every test for being genuinely distant. They dropped out at the expected wavelengths. Their colors matched high redshift predictions, but their brightness was a problem. To shine so brightly at such extreme distances, these objects would need to contain enormous amounts of luminous material. If they are galaxies, they formed too many stars too quickly. If they are powered by black holes, those black holes grew too massive too fast. Either explanation pushes against the boundaries of known physics. The researchers emphasize that these objects are candidates awaiting confirmation. Spectroscopic follow-up is needed to measure their exact distances and determine what powers their light. Some may turn out to be closer than they appear, interlopers masquerading as ancient sources. But the sheer number suggests many will prove genuine. 300 mysteries in a single survey, and this survey covered only a tiny fraction of the sky. If these objects are real, they represent an entirely new population of cosmic sources. They may be related to the little red dots, the mysterious compact objects that have puzzled astronomers since Webb's first observations. Or they may be something different entirely, a third category of ancient anomaly. What unites them is unexplained brightness. The early universe, according to standard models, should have been dimmer, fewer stars, smaller galaxies, less luminosity overall. Webb keeps finding the opposite. The young cosmos was ablaze with light from sources we cannot yet explain. Each mystery is an opportunity. If existing theories cannot account for these objects, new theories must be developed. Every observation that breaks a model is a chance to build a better one. The 300 bright unknowns are now targets for deeper study. Webb will return to some of them for longer observations. Ground-based telescopes will contribute their own data. Within the next few years, we may finally learn what these objects are, or we may discover that they are something even stranger than anyone has imagined. In all the galaxies astronomers have ever studied, stars dominate the light. Billions of nuclear furnaces burning hydrogen into helium, flooding space with photons across every wavelength. Gas and dust contribute some emission, but stars are always the brightest component, until Webb found an exception. Deep in the early universe, approximately 1 billion years after the Big Bang, the James Webb Space Telescope observed a galaxy unlike any other. Its light signature was dominated not by stars, but by gas. The hot, glowing clouds surrounding the galaxy outshone all the stellar light combined. This had never been seen before. Theoretical models had not predicted it. The observation forced astronomers to reconsider how some early galaxies formed and evolved. The galaxy appears to be in an unusual evolutionary state. Its gas is being heated by some powerful energy source, likely radiation from a central black hole or shockwaves from explosive star formation. This heated gas emits strongly in specific wavelengths that Webb's instruments are optimized to detect. What makes this discovery significant is not just the bright gas, but what it implies about the galaxy's future. If gas can dominate a galaxy's light output, that gas must eventually either form stars or be expelled. The balance between these outcomes determines whether the galaxy will grow or fade. In the modern universe, powerful black holes can heat surrounding gas so intensely that star formation shuts down entirely. Astronomers call this feedback, the process by which black holes regulate the growth of their host galaxies. The gas outshining galaxy may be caught in the act of this feedback process, a snapshot of a transitional state that normally passes too quickly to observe. Alternatively, the galaxy may represent a stage in formation that has no modern analog. The early universe had higher densities of gas, more frequent galaxy mergers, and different conditions for star formation. Perhaps some early galaxies went through phases where gas dominated temporarily before settling into star-dominated configurations. Either interpretation expands our understanding of galactic evolution. The discovery shows that the pathways from primordial gas cloud to mature galaxy are more diverse than previously recognized. Webb's spectroscopic capabilities made this detection possible. By splitting the galaxy's light into its component wavelengths, astronomers could identify the emission lines characteristic of hot gas and compare their strength to the continuous glow of starlight. The ratio was unmistakable. Gas was winning. The galaxy has been added to a growing list of anomalies that challenge conventional models. Each anomaly is a clue. Together, they are sketching a picture of the early universe that is richer, stranger, and more varied than textbooks describe. And the picture keeps getting more complex with every observation. In 2025, astronomers announced a discovery that left even seasoned researchers struggling to explain. A group of ancient galaxies, observed when the universe was less than 1 billion years old, were burning at temperatures that should not be possible. Heat in astronomy is usually measured through radiation. Hot objects emit light at shorter wavelengths. The hotter the object, the bluer and more energetic its glow. By analyzing the spectrum of a distant source, astronomers can estimate the temperature of the gas and stars it contains. The galaxies in question showed emission that implied extreme temperatures. Their gas was so hot, so energized, that standard heating mechanisms could not account for it. Stars alone could not provide enough energy. Even active black holes struggled to explain the observations. One researcher summarized the reaction with a simple question: how can all of this be happening? Several hypotheses have been proposed. The first involves unusually efficient star formation. If stars in the early universe formed in rapid bursts rather than steady streams, the combined radiation from millions of young, hot stars could temporarily superheat surrounding gas. This would produce the observed emission before the gas cooled and the signal faded. The second hypothesis involves black holes feeding at extreme rates. If the central black holes in these galaxies were accreting matter faster than the Eddington limit normally allows, they would produce intense radiation capable of heating gas to the observed temperatures. This would require physical conditions that are rare or impossible in the modern universe. The third hypothesis is more speculative. Perhaps the early universe contained energy sources we have not yet identified. Exotic particles, unusual physical processes, or interactions involving dark matter could have injected heat into these galaxies through mechanisms that do not operate today. None of these explanations are confirmed. Each has strengths and weaknesses. The observations are robust, replicated across multiple galaxies in the sample, but the interpretation remains contested. What is clear is that the early universe was more energetically extreme than models predicted. The furnaces burning in those ancient galaxies operated at efficiencies and intensities that push against the limits of known physics. This fits a broader pattern emerging from Webb's observations. Everywhere the telescope looks in the early cosmos, it finds more than expected. More galaxies, more black holes, more structure, more light, more heat. The young universe was not a quiet, simple place, gradually building toward complexity. It was already complex, already active, already filled with phenomena that challenge our understanding. The superhot galaxies are one more piece of that puzzle. They demand explanation, and finding that explanation may require revising fundamental assumptions about how matter, energy, and gravity interact at cosmic scales. The James Webb Space Telescope has opened a window into an era of the universe we could never see before. What we are finding through that window is rewriting the story of cosmic history in real time. For decades, astronomers imagined star formation as a slow, steady process. Gas clouds collapse gradually. Stars ignite one by one. Galaxies accumulate mass over billions of years, growing like trees adding rings. The James Webb Space Telescope has revealed a different picture. In the early universe, star formation did not proceed calmly. It exploded. Observations of distant galaxies show evidence of bursty star formation, periods of intense activity followed by quiet lulls. During a burst, millions of stars can ignite within a few million years. The combined radiation floods the galaxy with light, making it appear far brighter than a steady-state population of stars would produce. This explains one of Webb's biggest puzzles. Early galaxies appear too luminous for their age. If stars form steadily, there would not be enough of them to produce the observed brightness. But if stars formed in violent bursts, a galaxy could briefly shine far above its average level. Computer simulations support this interpretation. When researchers model the conditions of the early universe, they find that star formation naturally becomes bursty. The key factor is feedback, the way stars and black holes influence their surroundings. When a burst of star formation occurs, the young stars emit intense radiation. They also explode as supernovae after only a few million years. This radiation and these explosions heat the surrounding gas, blowing it outward and temporarily shutting down further star formation. The gas eventually cools and falls back toward the galaxy. When enough accumulates, another burst occurs. The cycle repeats, creating a pattern of peaks and valleys in the star formation rate. During a peak, a galaxy can appear 10 or even 100 times brighter than during a valley. If Webb happens to observe a galaxy during a burst phase, it will look anomalously luminous. This does not mean the galaxy contains more total mass than expected. It means we are catching it at a moment of maximum output. This interpretation is supported by chemical evidence. Burst star formation produces specific ratios of elements. Massive stars formed in bursts create large amounts of oxygen and nitrogen before exploding. The abundances of these elements in early galaxies match burst predictions better than steady-state predictions. The bursty model also explains the strange appearance of some early galaxies. During a burst, newly formed star clusters dominate the light. These clusters are compact and extremely blue, making the galaxy look clumpy and irregular. Between bursts, the galaxy may appear smoother as older, fainter stars dominate. Webb has captured galaxies in both states. Some early objects are smooth and relatively dim. Others are clumpy and blazingly bright. The diversity fits a picture where galaxies cycle through different phases rather than evolving along a single predictable track. There are limits to how much the bursty model can explain. Some early galaxies are so massive and so bright that even extreme bursts cannot fully account for them. These objects may require additional explanations, perhaps contributions from feeding black holes or exotic stellar populations. But for many of the surprisingly bright early galaxies, bursts provide a natural explanation that does not require breaking the standard model of cosmology. The universe did not necessarily form galaxies faster than expected. It formed them differently, in fits and starts, rather than steady growth. This insight changes how astronomers interpret their observations. A single snapshot of a distant galaxy does not tell the whole story. To understand that galaxy's true nature, scientists must consider what phase of its cycle it might be in. The James Webb Space Telescope captures moments frozen in time, but those moments are samples from dynamic processes that unfold over millions of years. Reading them correctly requires thinking about change, not just state. The early universe was a turbulent place. Stars were born in explosions. Galaxies flared and dimmed. Nothing was stable. Nothing was permanent. And the light from those chaotic times had to travel through a cosmos filled with obstacles before reaching us. For the first few 100 million years after the Big Bang, the universe was dark. Not because there was nothing to see, but because there was nothing that could carry light very far. Space was filled with a fog of neutral hydrogen. This fog absorbed ultraviolet and visible light, making the cosmos opaque. Photons could not travel freely. The universe was blind to itself. Then something changed. The first stars ignited. The first galaxies assembled. These new light sources emitted intense ultraviolet radiation that tore electrons away from hydrogen atoms, ionizing the gas and clearing the fog. This era is called reionization. It marks the transition from a dark, opaque universe to the transparent one we observe today. Understanding when and how reionization occurred is one of the central goals of early universe cosmology. The James Webb Space Telescope is providing answers, and some of them are surprising. One galaxy, observed just 330 million years after the Big Bang, showed an unexpected signature. Light from hydrogen was escaping from it more easily than it should have been able to during that foggy era. The fog around this galaxy had already cleared. This is puzzling, because reionization was supposed to be incomplete at that time. The surrounding intergalactic medium should have absorbed most of the escaping light. Instead, something had punched a hole in the fog, creating a bubble of ionized gas around the galaxy. The most likely explanation is that this galaxy, despite its young age, was already powerful enough to ionize its local environment. Its stars and possibly its central black hole were emitting enough ultraviolet radiation to keep a substantial volume of space clear. If true, this means reionization was patchier and more localized than simple models suggested. It did not proceed as a uniform wave sweeping across the universe. Instead, individual galaxies carved out their own bubbles, which eventually grew and merged until the entire cosmos was transparent. Webb has found similar evidence in other early galaxies. Some show strong signatures of escaping light, indicating cleared surroundings. Others show heavily absorbed spectra, suggesting they are still embedded in fog. The variation is exactly what a patchy reionization model predicts. This has implications for how we interpret observations of the early universe. Galaxies that appear bright may simply be the ones whose bubbles cleared first. Fainter galaxies may be equally massive but still surrounded by absorbing fog. Reionization also left permanent marks on the cosmos. The ionized gas between galaxies affects how light travels through the universe today. Measurements of distant quasars show absorption patterns that trace the end stages of reionization, occurring roughly 1 billion years after the Big Bang. Webb is pushing observations into the heart of this transition. It can see galaxies from before, during, and after reionization completed. By comparing these populations, astronomers can reconstruct how the fog burned away and what sources were responsible. The leading candidates are ordinary hot stars. Massive young stars emit copious ultraviolet radiation. In a starburst galaxy, the combined output of millions of such stars could ionize enormous volumes of surrounding gas. But black holes may have played a role too. Active galactic nuclei, powered by matter falling into supermassive black holes, emit even more intense radiation than stars. A single bright quasar could clear a bubble stretching millions of light years across. Webb is finding evidence for both contributors. The early universe was filled with star-bursting galaxies and nascent black holes, all working together to lift the cosmic fog and let light flow freely. The transition from darkness to light was one of the most important moments in cosmic history. We are now watching it unfold in detail for the first time. The universe began with almost nothing. Hydrogen, helium, trace amounts of lithium. That was the entire periodic table for millions of years. Everything else, carbon, oxygen, iron, gold, was forged later. Inside, stars. In supernova explosions. Through the collisions of dead stellar cores, heavy elements are the products of cosmic recycling, built up gradually over billions of years, or so astronomers believed. The James Webb Space Telescope has found heavy elements in galaxies so young they should not contain them yet. Oxygen appears in spectra from galaxies less than 400 million years old. Nitrogen shows up in unusual abundances. Dust, which requires heavy elements to form, exists in galaxies that barely had time to produce their first generation of stars. This presents a timing problem. Massive stars produce heavy elements when they explode as supernovae, but even the shortest-lived massive stars take a few million years to exhaust their fuel and die. Then the expelled elements must mix into surrounding gas and be incorporated into new stars or dust grains. The standard timeline allowed for this process to take hundreds of millions of years before heavy elements became abundant. Webb is finding them far earlier. Several explanations have been proposed. The first involves the efficiency of early supernovae. If the first generation of stars was dominated by extremely massive objects, they would have lived even shorter lives than typical massive stars today. Their rapid deaths could have seeded the cosmos with heavy elements on compressed timescales. The second explanation involves hypernovae, explosions even more powerful than ordinary supernovae. These events produce larger quantities of certain elements and distribute them across greater volumes of space. If hypernovae were common in the early universe, they could have enriched galaxies faster than standard models predict. The third explanation involves the mixing process itself. Perhaps heavy elements spread through early galaxies more efficiently than in modern ones. The smaller sizes and higher densities of early galaxies could have allowed expelled material to be recycled into new stars more quickly. Evidence supports all three possibilities to varying degrees. Some early galaxies show elemental ratios consistent with enrichment by very massive stars. Others show signatures of unusually energetic explosions. The details vary from galaxy to galaxy, suggesting that multiple pathways contributed. The presence of dust is particularly significant. Dust grains are tiny solid particles, typically made of silicates or carbon compounds. They form when heavy elements ejected by dying stars cool and condense in the expanding debris clouds. Finding dust in galaxies less than 300 million years old means that not only did stars produce heavy elements quickly, but those elements had time to cool, condense, and form solid particles. The entire cycle, from star birth to star death to grain formation, occurred within an astonishingly short window. Webb detects dust by its effect on galaxy colors. Dust absorbs blue light and re-emits it at longer wavelengths. Dusty galaxies appear redder than their stellar populations alone would suggest. Several of the most distant galaxies Webb has observed show exactly this reddening. The rapid appearance of heavy elements matters for more than academic reasons. Heavy elements are essential for planet formation. Rocky planets like Earth are made almost entirely of iron, silicon, oxygen, and other products of stellar nucleosynthesis. Without heavy elements, there are no terrestrial worlds. If heavy elements appeared earlier than expected, habitable planets could have formed earlier too. The window for life in the universe may extend further back in time than anyone realized. Before the James Webb Space Telescope launched, astronomers had detailed predictions for what it would find. These predictions came from cosmological simulations, enormous computer models that track the evolution of matter from the Big Bang to the present day. Simulations are one of the most powerful tools in modern astrophysics. They encode the laws of physics, gravity, hydrodynamics, radiation, and nuclear reactions, and let them play out over billions of simulated years. The results show how gas collapses into halos, how halos merge into galaxies, and how galaxies grow and evolve. The best simulations reproduce many features of the observed universe with remarkable accuracy. The large-scale distribution of galaxies, the properties of galaxy clusters, the abundances of different galaxy types, all match observations reasonably well. But when Webb began observing the early universe, the simulations started to break down. The galaxies Webb found were more massive, more luminous, and more numerous than simulations predicted. The black holes were bigger, the structures were more complex. At nearly every point of comparison, reality exceeded the simulations. This does not mean the simulations are useless. It means they are incomplete. Something about the physics encoded in them does not fully capture what happened in the first billion years of cosmic history. Identifying what is missing is now a major focus of theoretical research. Several possibilities are under investigation. The first involves star formation efficiency. Simulations assume that only a fraction of available gas converts into stars during any given time period. This efficiency is calibrated to match observations of nearby galaxies, but perhaps early galaxies converted gas into stars more efficiently, either because the gas was denser or because feedback processes were weaker. The second involves black hole seeding. Simulations typically start with small black hole seeds, the remnants of ordinary massive stars. These seeds then grow through accretion and mergers. But if black holes started larger, through direct collapse or other mechanisms, they would reach supermassive status faster. The third involves feedback itself. Stars and black holes inject energy into surrounding gas, heating it and slowing further star formation. If this feedback was less effective in the early universe, galaxies could have grown more rapidly before self-regulation kicked in. Some researchers are exploring more radical possibilities. Perhaps the laws of physics operated slightly differently at early times. Perhaps dark matter has properties that simulations do not account for. Perhaps entirely new processes were at work that have no analog in the modern universe. Testing these ideas requires comparing updated simulations against Webb data. This is an iterative process. Scientists adjust the parameters in their models, run new simulations, and check whether the results match observations better than before. Progress has been made. Newer simulations that allow for bursty star formation and more efficient early black hole growth reproduce some of Webb's surprises, but full agreement has not been achieved. The gap between simulation and reality persists. This gap is not a failure, it is an opportunity. Every discrepancy between prediction and observation is a clue pointing toward missing physics. Resolving these discrepancies will deepen our understanding of how the cosmos works. The universe is the ultimate laboratory. Webb is providing the data, simulations are providing the hypotheses. Together, they are converging on a more complete picture of cosmic history. There is a limit to how far even the James Webb Space Telescope can see on its own. Distant objects are faint, their light stretched thin by the expansion of the universe. Beyond a certain distance, individual stars and small galaxies disappear into the background noise. But nature has provided a workaround. Massive objects bend light. Galaxy clusters, containing hundreds or thousands of galaxies, plus vast amounts of dark matter, curve the fabric of space around them. Light passing through this curved space is bent, focused, and magnified. This effect is called gravitational lensing. It was predicted by Einstein over a century ago and has been observed many times since, but the James Webb Space Telescope is exploiting it in ways never before possible. When a distant galaxy sits directly behind a massive foreground cluster, the cluster acts as a natural telescope. The background galaxy's light is magnified by factors of 10, 50, sometimes over 100. Details that would otherwise be invisible become detectable. Webb has used gravitational lensing to study some of the faintest and most distant objects in the universe. Individual stars and galaxies billions of light-years away have been observed through these cosmic magnifying glasses. Without lensing, these stars would be far too dim to detect. One famous example is a star nicknamed Earendel. It was first spotted by the Hubble Space Telescope and later observed by Webb. Earendel existed when the universe was less than 1 billion years old. It was magnified by a foreground cluster to the point where its light could be distinguished from the surrounding galaxy. Webb's observations revealed Earendel's color and temperature. It appears to be a massive hot star, possibly part of a binary system. Studying individual stars at such extreme distances provides direct information about the stellar populations of early galaxies. Another lensed object is a galaxy called the Sunrise Arc. It appears as a long, curved streak in Webb images, stretched by the gravitational field of a foreground cluster. Within this arc, astronomers have identified multiple star clusters and possibly even globular clusters, dense balls of ancient stars. Gravitational lensing is also being used to search for the elusive population 3 stars. These first-generation stars would have been extremely bright, but existed only briefly before exploding. Catching one through a lensing magnification could provide the first direct evidence of the earliest stellar generation. The technique has limitations. Lensing only works when objects happen to align along our line of sight. The magnification is strongest along specific curves called caustics, and objects must fall near these curves to benefit fully. Much of the distant universe remains unmagnified and therefore invisible. But surveys are identifying more and more useful lensing clusters. Each one provides a window into a different patch of the distant cosmos. By combining observations through multiple cosmic telescopes, astronomers are assembling an increasingly detailed picture of the early universe. The universe is not just something to study, it is also an instrument for studying itself. Webb, working in partnership with nature's own lenses, is seeing further than any telescope could alone. When observations consistently defy predictions, scientists face a choice. Either the observations are wrong, or the theories are incomplete. The James Webb Space Telescope has produced observations that survive every test of accuracy. The data is reliable. The measurements are reproducible. Independent teams analyzing the same targets reach the same conclusions. That leaves the theories. The standard model of cosmology has been extraordinarily successful. It explains the cosmic microwave background, the distribution of galaxies, the abundances of light elements, and the accelerating expansion of the universe. It is built on well-tested physics, general relativity, and the standard model of particle physics, plus a few additional ingredients like dark matter and dark energy. But Webb's discoveries are straining this framework. Galaxies too massive, black holes too large, structures too complex, all appearing too early in cosmic history. The Hubble tension remains unresolved. The nature of dark matter is still unknown. Physicists are exploring what new ingredients might be needed to reconcile observations with theory. One possibility is early dark energy. Standard cosmology includes dark energy, the mysterious force accelerating the expansion of the universe today. But what if dark energy behaved differently in the past? A brief burst of extra dark energy in the early universe could have accelerated expansion temporarily, affecting the formation of structures and potentially resolving the Hubble tension. Another possibility involves modifications to gravity. General relativity has been tested extensively at solar system scales, but it has never been tested directly at cosmological scales in the early universe. Some alternative theories of gravity predict different behavior under extreme conditions, which could affect how structures formed and grew. A third possibility concerns dark matter itself. The standard assumption is that dark matter is cold, made of heavy, slow-moving particles that clump on small scales. But what if dark matter is warm or fuzzy? Lighter particles moving faster would smooth out small-scale structures, potentially explaining the elongated shapes of early galaxies and other anomalies. A fourth possibility is even more exotic. Some theorists have proposed that the constants of nature, like the mass of the electron or the strength of gravity, may have varied slightly in the early universe. Such variations could have profound effects on star formation, black hole growth, and chemical evolution. None of these ideas are confirmed. They are hypotheses being tested against data. Each makes specific predictions that can be compared with observations. As Webb continues to gather information and other experiments probe different aspects of the cosmos, some hypotheses will be ruled out and others will gain support. This is how science progresses. Anomalies drive discovery. When the data refuses to fit the theory must change. The process can take years or decades, but it eventually produces a deeper understanding. The James Webb Space Telescope may have revealed that our current picture of the universe is incomplete. That is not a crisis. It is an invitation. The cosmos is offering clues to new physics, and scientists are racing to decode them. 14 billion years ago, there was no Earth, no solar system, no Milky Way, just a hot, dense fog of particles expanding outward from an initial singularity. Then gravity began its work. Matter clumped. Stars ignited. Heavy elements were forged and scattered. Galaxies assembled. One ordinary spiral galaxy, in one ordinary corner of one ordinary supercluster, gave rise to a yellow dwarf star surrounded by rocky planets. On the third of those planets, chemistry became biology. Biology became consciousness. Consciousness built telescopes, and those telescopes have now looked back to the beginning. The James Webb Space Telescope is not just observing distant objects, it is observing our origins. Every heavy atom in your body was forged in a star that lived and died billions of years ago. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it came from stellar furnaces scattered across cosmic time. When Webb finds heavy elements in galaxies less than 400 million years old, It is finding the earliest ancestors of the atoms that would someday become you. When it observes the first stars and black holes, it is witnessing the processes that set everything else in motion. This is not abstract knowledge, it is personal. You are made of materials that were assembled in the first chapters of cosmic history. Understanding those chapters is understanding where you came from. But Webb's discoveries also carry a more unsettling implication. If our understanding of the universe is incomplete, so is our understanding of our place in it. The standard cosmological model provided a coherent narrative. The universe began with a big bang, expanded and cooled, formed structures through gravity, and evolved predictably toward its current state. We could calculate the age of the cosmos, the density of matter, the fate of galaxies billions of years in the future. Now that narrative has cracks. The Hubble tension suggests something is missing from our equations. The impossible early galaxies suggest our timeline is wrong. The nature of dark matter and dark energy remains unknown. We do not know the full story of the universe. We thought we did. We were wrong. This uncertainty is uncomfortable, but also thrilling. It means there is more to discover. The cosmos has not revealed all its secrets. Future generations will learn things about reality that we cannot even imagine today. The James Webb Space Telescope is one chapter in a long story of discovery. Galileo pointed a small tube at the sky and saw moons orbiting Jupiter. Hubble proved that galaxies exist beyond our own. Now Webb is rewriting the first pages of cosmic history. What comes next? Larger telescopes, better instruments, new ideas. The questions Webb has raised will be answered, and those answers will raise new questions. This process has no end. The universe is infinite in its capacity to surprise us. And somewhere in that infinite cosmos, on a small rocky world orbiting an ordinary star, beings made of ancient stardust are looking up and wondering what it all means. The James Webb Space Telescope will not operate forever. Its fuel will run out. Its instruments will degrade. Someday, perhaps in 20 years, perhaps a bit longer, it will fall silent. But the exploration will continue. Already, new missions are being planned. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will survey the sky with a field of view 100 times wider than Webb's. It will map the distribution of galaxies across cosmic time, measuring the effects of dark energy and searching for new gravitational lenses. Ground-based observatories are advancing as well. The extremely large telescope in Chile, with a mirror nearly 40 meters across, will have resolution sharper than Webb's in certain wavelengths. It will study the atmospheres of exoplanets and peer into the hearts of distant galaxies. Future space telescopes are being conceptualized. Some would observe in wavelengths Webb cannot access. Others would use multiple spacecraft flying in formation to create effective mirrors kilometers across. The technology exists, at least in principle, to build instruments far more powerful than anything we have today. Each new telescope will build on what Webb has discovered. The impossible galaxies, the overmassive black holes, the mysterious little red dots, all will be studied in greater detail. Questions that Webb raised but could not answer will be addressed by its successors. The biggest questions remain open. What is dark matter? What is dark energy? Why does the universe exist at all? These are not just astronomical questions. They are questions about the fundamental nature of reality. Answering them may require more than telescopes. Particle accelerators search for dark matter candidates in laboratory collisions. Gravitational wave detectors listen for ripples in space-time from merging black holes. Theorists develop mathematical frameworks that might unify gravity with quantum mechanics. All these efforts are connected. Discoveries in one field inform questions in another. A detection of dark matter particles would transform how cosmologists model galaxy formation. A breakthrough in quantum gravity could explain what happened in the first instance after the Big Bang. Science advances as a collective enterprise. No single telescope, no single experiment, no single theorist will solve the mysteries of the cosmos alone. Progress comes from combining many observations, many experiments, many ideas across generations. The James Webb Space Telescope is a magnificent achievement. It represents decades of work by thousands of scientists and engineers across multiple countries. It has exceeded every expectation and transformed our view of the universe. But it is also a beginning. Every answer it provides leads to new questions. Every mystery it solves reveals deeper mysteries behind it. The universe is not running out of secrets to share. Humanity has been looking at the stars for as long as there have been humans. We have gone from naked eye observations to orbiting infrared telescopes in a few thousand years. What will the next few thousand bring? The journey continues. The questions multiply. And somewhere out there, the cosmos waits to be understood. We have traveled far. From the moment Webb opened its golden eyes to the edge of observable time. From galaxies that should not exist to black holes that grew too fast. From stars powered by darkness to a universe that may be spinning. Every chapter of this journey revealed something unexpected. The cosmos is not what we thought it was. The timeline is broken. The models are incomplete. The questions are multiplying faster than the answers. And yet, here is the strangest truth of all. We can see any of this at all. 14 billion years of cosmic history, compressed into photons traveling through expanding space, captured by mirrors and sensors, built by creatures who have existed for less than 1/1,000,000th of that time. The universe has handed us its autobiography, written in light, and we have learned to read it. That ability is not guaranteed. There was no reason the cosmos had to be comprehensible. No law required that physics be consistent enough for science to work. No principle demanded that beings would evolve who could ask where they came from. Yet here we are, asking, searching, finding. The James Webb Space Telescope did not break the universe. It revealed that the universe was always stranger than we knew. The cracks were always there, hidden by the limits of previous instruments. Webb simply has the vision to see them. What fills those cracks? We do not know yet. New physics, perhaps. New particles, new forces, new relationships between matter, energy, space, and time. The next generation of scientists will spend their careers exploring possibilities we cannot yet imagine. But one thing is certain, the story is not over. It may never be over. The universe is vast beyond comprehension, old beyond intuition, complex beyond any single mind's ability to grasp, and it is still revealing itself, one photon at a time. You have spent 2 hours at the edge of reality. You have seen the first light, the impossible galaxies, the monsters in the dark. You have watched stars explode and black holes run and the fabric of space twist under forces we barely understand. Now look up. On a clear night, away from city lights, you can see a few thousand stars with your naked eyes. Each one is a furnace burning hydrogen into helium, forging the elements that will someday become planets, oceans, life. Beyond those stars are billions more, gathered into a spiral arm of a galaxy containing hundreds of billions of stars total. Beyond that galaxy are billions more galaxies, stretching outward in every direction, filling a volume of space so large that light itself cannot cross it in the time the universe has existed. And beyond the light we can see, there may be more, regions of space that have expanded away from us so fast that their light will never reach Earth, no matter how long we wait. We are small, unimaginably small. A single species on a single planet orbiting a single star in a single galaxy among trillions. And yet we built a telescope that can see to the beginning of time. We asked where we came from. The universe is answering. The answer is stranger than anyone expected. It will take generations to fully understand. But understand it we will, because that is what we do. We look, we question, we learn. The James Webb Space Telescope has shown us that the universe is full of mysteries. That is not a reason for despair. It is a reason for wonder. The beginning of everything is still being written, and we are the ones holding the pen. Galaxies are supposed to be busy in the early universe. Gas is plentiful. Gravity is pulling everything together. Collisions are frequent. The cosmic environment demands activity. Stars should be forming everywhere, all the time. So when the James Webb Space Telescope found galaxies that had stopped, astronomers struggled to explain it. They call them quiescent galaxies, sleeping beauties, objects that have ceased forming stars entirely, settling into a quiet dormancy that should not be possible so early in cosmic history. In the modern universe, quiescent galaxies are common. Many massive elliptical galaxies exhausted their gas supplies billions of years ago. Without raw material, star formation cannot continue. These galaxies glow red with the light of old, cool stars, aging gracefully in cosmic retirement. But building a quiescent galaxy takes time. A galaxy must first form many generations of stars. Those stars must consume or expel the available gas. Feedback from supernovae and black holes must heat whatever remains, preventing it from cooling and collapsing. Only after billions of years of activity can a galaxy truly rest. Webb found quiescent galaxies when the universe was less than 2 billion years old. Some appeared to have stopped forming stars when the cosmos was barely 1 billion years old. The timeline does not work. How does a galaxy exhaust itself so quickly? Several mechanisms have been proposed. The first involves supermassive black holes. When a black hole feeds aggressively, it releases enormous amounts of energy. This energy can heat surrounding gas to temperatures so high that it cannot collapse into stars. A sufficiently powerful black hole could shut down an entire galaxy's star formation in a relatively short time. Evidence supports this idea. Many of the early quiescent galaxies Webb observed show signs of past black hole activity. Their central regions contain the remnants of active galactic nuclei, now quiet but once blazing with radiation. The second mechanism involves galaxy mergers. When two galaxies collide, the interaction can trigger intense bursts of star formation. These bursts consume gas rapidly, burning through the available fuel in a fraction of the time steady formation would take. After the merger completes, little gas remains. Some early quiescent galaxies show disturbed shapes consistent with recent mergers. Their stars are distributed in ways that suggest gravitational disruption. The collision that created them may also have killed them. The third mechanism is environmental. Galaxies do not exist in isolation. They cluster together in groups and filaments. In dense environments, interactions with neighbors can strip gas away, removing the fuel for star formation without consuming it internally. Webb has observed early galaxy clusters where quiescent members are more common than in the surrounding field. The environment appears to accelerate the transition from active to dormant. What makes these sleeping beauties significant is not just their existence, but their implications for galaxy evolution. If galaxies can shut down this early, the processes that regulate star formation must be more powerful and more rapid than models assumed. The standard picture of galaxy evolution describes a gradual transition. Galaxies form stars actively for billions of years, then slowly wind down as gas depletes. Webb is showing that some galaxies skip the slow decline entirely, slamming on the brakes almost as soon as they finish accelerating. This changes how astronomers think about cosmic history. The diversity of galaxies in the early universe is greater than expected. Some were forming stars frantically, others had already stopped. The young cosmos was not a uniform sea of activity, but a patchwork of different evolutionary states. The sleeping beauties are now targets for deeper study. Understanding why they stopped will reveal what forces control star formation across cosmic time. Every dormant galaxy is a puzzle, and solving it will illuminate the lives of all galaxies, including our own. But dormancy is only one fate. Other early galaxies met more violent ends, or, more accurately, violent beginnings. Galaxies do not grow in isolation. They grow by eating each other. This process is called hierarchical assembly. Small galaxies form first, then merge into larger ones. Those merge again into still larger structures. Over billions of years, collisions build the massive galaxies we see today. The Milky Way itself is a product of countless mergers. Streams of stars in our galaxy's halo trace the orbits of smaller galaxies that were torn apart and absorbed long ago, and the process continues. In about 4 billion years, the Milky Way will collide with Andromeda, our nearest large neighbor. Astronomers expected mergers to be important in the early universe, but they underestimated how important. The James Webb Space Telescope has revealed that collisions were happening faster, more frequently, and more violently than models predicted. In deep field images, Webb captured galaxies in the act of merging, distorted shapes, tidal tails, bridges of stars connecting separate cores. These signatures of gravitational interaction appear throughout the early cosmos, far more commonly than simulations suggested. One spectacular example involves a group of 5 galaxies observed when the universe was less than 1 billion years old. All 5 are interacting, their structures warped by mutual gravitational pull. Within a few 100 million years, they will likely merge into a single massive object. Finding such a dense group so early challenges models of structure formation. Galaxies were supposed to be more spread out at that time, with fewer opportunities for close encounters. The universe had not had enough time to gather so many objects into such a small volume, yet there they are, 5 galaxies dancing toward their mutual destruction, building something larger from their combined wreckage. Mergers have profound effects on the galaxies involved. The gravitational disturbance compresses gas clouds, triggering bursts of star formation. Central black holes are fed by infalling material, growing rapidly during the chaos. The entire structure of both galaxies is reshuffled, often transforming spirals into ellipticals. Webb has observed all these effects in early merging systems. Starbursts light up the collision zones. Black holes flare with activity. Morphologies shift from ordered to chaotic. The frequency of early mergers helps explain some of Webb's other surprises. If galaxies were merging more often, they would have grown faster than isolated evolution allows. The massive early galaxies that seemed impossible might simply be the products of rapid assembly through multiple collisions. Similarly, the overmassive early black holes could have grown through mergers. When 2 galaxies combine, their central black holes eventually find each other and merge as well. A series of such events could build a supermassive black hole faster than feeding alone would permit. Mergers also explain some of the chemical enrichment Webb has observed. When galaxies collide, their gas mixes. Heavy elements produced in one galaxy spread into the other. The combined system inherits the chemical history of both progenitors. But mergers create problems too. They should destroy delicate structures like spiral arms. Yet Webb has found early spirals that appear to have survived interactions. Either these galaxies avoided collisions entirely, or spiral patterns can reform faster than astronomers believed. The early universe was a violent place. Galaxies were closer together, moving faster, colliding more often. The structures we see today were forged in that chaos, assembled from the wreckage of countless smaller systems. Webb is watching this assembly in progress, capturing snapshots of a cosmic construction site, where the building materials are entire galaxies. Science occasionally discovers something that does not fit any existing category, an object so strange that it demands a new classification entirely. The James Webb Space Telescope may have found such objects, and they are forcing astronomers to expand their cosmic taxonomy. The little red dots, those mysterious compact sources scattered throughout Webb's deep field images, continue to defy explanation. Some are clearly galaxies with active black holes. Others show properties that match no known type of astronomical object. Recent analyses suggest that a subset of the little red dots might represent something entirely new, not galaxies, not quasars, not stars in any conventional sense, something in between. Researchers have proposed calling them black hole stars. The concept is straightforward in principle. Imagine a supermassive black hole surrounded by a dense envelope of gas. The black hole is feeding, pulling material inward. As that material falls, it heats up and radiates intensely. But unlike a typical active galactic nucleus, where the radiation escapes freely, this system is wrapped in so much gas that most of the light is absorbed and re-emitted at longer wavelengths. The result would look like a single luminous object, compact and red, with spectral signatures that blend characteristics of stars and black holes. It would not fit cleanly into existing categories because it genuinely is something different. Black hole stars would only form under specific conditions. The early universe, with its dense gas supplies and rapidly growing black holes, provides exactly those conditions. In the modern cosmos, galaxies are too diffuse and black holes too settled to produce such hybrids. This explains why the little red dots appear only at high redshifts. They are relics of a transitional phase in cosmic history, objects that existed briefly during the chaotic assembly of the first galaxies and then disappeared as conditions changed. Evidence supporting this interpretation comes from spectroscopy. Some little red dots show emission lines characteristic of gas orbiting a massive central object at extreme speeds. But they also show absorption features that suggest light is passing through a thick, surrounding medium. The combination is unusual and matches black hole star predictions. Other little red dots may have different explanations. The population is diverse, and multiple types of objects probably contribute. Some are likely ordinary active galaxies, viewed through unusual angles or dust configurations. Others may be something else entirely. What is certain is that Webb has opened a window into a regime of cosmic objects that previous telescopes could not access. The early universe contained phenomena that do not exist today. Understanding them requires expanding our frameworks beyond what modern observations alone could teach us. Black hole stars, if confirmed, would fill an important gap in cosmic evolution. They would represent a stage between the first stellar mass black holes and the supermassive monsters at the centers of mature galaxies. They would explain how black holes grew so large so quickly, feeding in obscured cocoons before emerging as the quasars we observe. The universe may contain more than galaxies, stars, and black holes as separate categories. It may contain hybrids, transitional forms, objects that blur the boundaries we draw for convenience. Webb is teaching us that those boundaries are less fixed than we assumed. When European scientists first encountered the platypus, they thought it was a hoax, a mammal with a duck's bill, a beaver's tail, and venomous spurs on its hind legs. Surely someone had stitched together parts from different animals as a joke. The platypus was real. It simply did not fit the categories scientists had built from their limited experience. Nature had produced something that combined features in unexpected ways. The James Webb Space Telescope has found the cosmic equivalent, galaxies so strange that astronomers have nicknamed them platypus galaxies. These objects combine properties that do not normally appear together. They show the compact size of early quiescent galaxies but the active star formation of starbursts. They have the red colors of dusty systems but the emission lines of pristine gas. They display the brightness of massive galaxies but the chaotic structures of recent mergers. No single explanation accounts for all their features. Like the biological platypus, they seem to be assembled from parts that belong to different categories entirely. A team analyzing Webb data identified 9 such objects in deep survey fields. All existed within the first 1.5 billion years after the Big Bang. Their spectra showed unusual peaked emission at specific wavelengths, unlike anything seen in nearby galaxies. The physical interpretation remains uncertain. One hypothesis suggests these are galaxies caught in an extremely brief transitional phase, changing so rapidly that they display characteristics of multiple evolutionary stages simultaneously. If this phase lasts only a few million years, catching galaxies in it would require observing many candidates. Another hypothesis proposes that early universe conditions allowed combinations of properties that cannot coexist today. Higher gas densities, more frequent interactions, and stronger radiation fields might have produced genuinely novel objects that have no modern analogues. A third hypothesis suggests that some platypus galaxies contain multiple components blended together by limited resolution. What appears as one object might actually be 2 or 3 overlapping sources, each contributing different spectral features to the combined measurement. Resolving these hypotheses requires deeper observations. Webb can return to these targets with longer exposures and more detailed spectroscopy. Higher resolution imaging might separate blended sources. More precise measurements might reveal which features come from which physical processes. The platypus galaxies illustrate a broader lesson. Categories are human inventions. We divide the universe into stars and galaxies, active and quiescent, spirals and ellipticals, because these divisions help us organize knowledge. But the universe does not consult our categories before producing objects. Early cosmic history was a time of experimentation. Conditions were different. Processes operated at different rates. Objects formed that explored regions of parameter space that later became inaccessible. Some of those objects do not match anything in our existing taxonomy. Rather than forcing them into ill-fitting categories, astronomers are learning to let the objects define themselves. The platypus galaxies are platypus galaxies. They deserve study on their own terms. Webb is revealing that the universe was more creative than we gave it credit for. The early cosmos tried many configurations, many combinations, many experiments. Most did not survive to the present day, but their light is still traveling toward us, carrying evidence of paths not taken. The James Webb Space Telescope was not built only to study the distant universe. It was also designed to examine worlds much closer to home, planets orbiting other stars. And what it has found there is just as surprising. Exoplanets were once purely hypothetical. The first confirmed detection came only in 1995. Since then, thousands have been discovered, orbiting stars throughout the galaxy. Rocky planets, gas giants, ice worlds, lava planets. The diversity is staggering, but finding a planet is only the first step. Understanding what that planet is actually like requires studying its atmosphere, and that is extraordinarily difficult. Planets do not emit much light of their own. They are overwhelmed by the glare of their host stars, outshone by factors of millions or billions. Detecting the faint signature of planetary atmospheres against that glare requires exceptional precision. Webb has that precision. By observing planets as they pass in front of their stars, astronomers can measure how starlight filters through planetary atmospheres. Different molecules absorb light at different wavelengths, leaving fingerprints in the spectrum. Webb has detected water vapor in the atmospheres of multiple exoplanets. It has found carbon dioxide, methane, sulfur dioxide, and other compounds. Each detection adds to our understanding of how atmospheres form and evolve. One planet in particular has drawn intense attention. It orbits a cool red dwarf star, about 120 light-years from Earth. This world is roughly 8 times more massive than Earth and sits in its star's habitable zone, where liquid water could theoretically exist on the surface. Webb's observations detected carbon-bearing molecules in this planet's atmosphere. The specific mix of chemicals raised the possibility that the planet might have an ocean beneath a hydrogen-rich sky. An ocean would make this world a prime candidate for habitability. The interpretation is contested. Other scientists argue that the atmospheric signatures could be produced without liquid water. The planet might be a gas-dominated world with no solid surface at all. More observations are needed to distinguish between possibilities. But the mere fact that we can ask such questions represents a revolution. A generation ago, detecting atmospheres on planets orbiting other stars was science fiction. Now it is routine science, limited mainly by telescope time rather than technical capability. Webb has also observed planets that challenge our understanding of atmospheric physics. One gas giant orbiting extremely close to its star appears to have an atmosphere shaped like a football rather than a sphere. Gravitational tides from the star are distorting the planet's entire gaseous envelope. Another planet shows atmospheric chemistry that does not match any model predictions. The expected molecules are absent, unexpected ones are present. Something about the planet's formation or evolution produced conditions that existing theories cannot explain. Exoplanet science is still young. Each new observation expands the known range of planetary possibilities. Every atmosphere studied adds data points to our understanding of how worlds work. The ultimate goal is finding signs of life. Certain combinations of atmospheric gases, like oxygen alongside methane, would be difficult to explain without biological processes. Webb may not be sensitive enough to detect such biosignatures on Earth-sized planets, but future telescopes will be. For now, Webb is laying the groundwork, characterizing atmospheres, testing models, discovering the unexpected, preparing for the day when we might finally answer whether we are alone. There is a boundary to the observable universe, not because space ends, but because light does. The universe is approximately 13.8 billion years old. Light travels at a finite speed. Therefore, we can only see objects whose light has had time to reach us since the beginning of cosmic time. This defines the observable universe, a sphere centered on Earth with a radius of about 46 billion light-years. Beyond that sphere, there may be more space, more galaxies, more everything, but their light has not arrived yet. For all practical purposes, they do not exist for us. The James Webb Space Telescope is pushing observations toward that boundary. The most distant galaxies it has detected existed when the universe was only a few 100 million years old. Light from those objects has been traveling for over 13 billion years to reach Webb's mirrors. But there is a deeper limit. Before a certain point in cosmic history, the universe was opaque. Hot plasma filled all of space, scattering light in every direction. Photons could not travel in straight lines. No telescope, no matter how powerful, can see through that primordial fog. This curtain fell approximately 380,000 years after the Big Bang. Before that moment, the universe is hidden from direct observation. We can infer what happened through theory and indirect evidence, but we cannot image it. Webb is operating close to this fundamental limit. The earliest objects it can possibly detect formed just after the fog lifted, when the first stars began to shine. Going further back requires different methods entirely. Gravitational waves offer one alternative. Ripples in space-time from the earliest moments of the universe might still be propagating today. Detecting them would provide information about conditions before light could travel freely. Neutrinos offer another. These ghostly particles interact so weakly with matter that they could have escaped the primordial plasma when photons could not. A cosmic neutrino background should exist, carrying information from even earlier times. Detecting it is beyond current technology, but not beyond imagination. The deepest limit of all concerns the Big Bang itself. What happened at the very beginning, when all of space was compressed into a single point? Current physics breaks down at that moment. General relativity and quantum mechanics give contradictory answers. A theory of quantum gravity, not yet developed, would be needed to describe those conditions. We may never know what happened in the first fraction of a second. The information may be fundamentally inaccessible, hidden behind horizons of physics we cannot cross. This is humbling. The universe has boundaries not just in space, but in knowledge. Some questions may have answers we can never reach. Some mysteries may remain mysteries forever. And yet, consider how far we have come. A century ago, we did not know other galaxies existed. 50 years ago, we could not detect planets around other stars. 20 years ago, we could not see the first billion years of cosmic history. The boundaries keep moving. Each generation pushes further than the last. What seems impossible today becomes routine tomorrow. Webb cannot see to the beginning of time, but it can see further than anything before it. And whatever comes next will see further still. Every culture tells stories about where the universe came from. Creation myths, origin tales, narratives that explain how everything began and why it looks the way it does. Science tells such a story too. It is called cosmology. And the James Webb Space Telescope is forcing us to revise it. The old story went like this. 13.8 billion years ago, the universe began in an unimaginably hot, dense state. It expanded and cooled. After about 380,000 years, atoms formed and light could travel freely. Gravity slowly gathered matter into clumps. The first stars ignited after a few 100 million years, small and isolated. Galaxies assembled gradually over billions of years, growing through steady accretion and occasional mergers. Black holes formed from dead stars and grew slowly through feeding. The universe evolved from simple to complex, from chaos to structure, in a stately progression toward its current state. That story was elegant. It was consistent. It explained most observations with remarkable success. But Webb has complicated it. The new story is still taking shape. Its outlines are emerging from thousands of observations, hundreds of papers, countless hours of analysis and debate. Here is what we can say so far. The universe began the same way. The Big Bang, the expansion, the cooling, the formation of atoms, these parts remain unchanged. But what happened next was faster and stranger than we thought. The first stars may have been monsters, hundreds or thousands of times more massive than any star today. They may have been powered by dark matter annihilation rather than nuclear fusion. They lived briefly and died violently, seeding the cosmos with heavy elements on timescales we did not expect. Black holes may have formed before galaxies, growing rapidly in obscured cocoons, reaching supermassive status, while the stars around them were still assembling. The relationship between black holes and galaxies may be the reverse of what textbooks describe. Galaxies themselves formed faster, grew larger, and organized sooner than models predicted. Spiral arms appeared when they should have been impossible. Quiescent galaxies shut down when they should have been thriving. Star formation proceeded in explosive bursts rather than steady streams. The universe may have a preferred direction. Dark matter may have properties we have not accounted for. The rate of cosmic expansion may vary in ways our equations do not capture. None of this overthrows the Big Bang model. The basic framework holds, but the details are being rewritten in real time, chapter by chapter, as Webb sends back data from the edge of observable time. This is how science works. Stories are provisional, evidence accumulates, narratives adjust. The goal is not to find a final, unchanging truth, but to build ever better approximations of what actually happened. The story we tell now is more complex than the one we told before. It has more characters, more subplots, more unresolved mysteries. It is messier and less satisfying in some ways. But it is also closer to reality. And reality, however strange, is always more interesting than our simplified models of it. The James Webb Space Telescope has given us a new creation story. It is incomplete. It will be revised again. But for now, it is the best account we have of how everything began. And that is worth celebrating.